So continuing on with our overview, now that we've talked about what reactive programming is, the principles, the 4 principles, now that we've talked a bit about the reactive streams, APIs, RxJava, Project Reactor, let's see how the principles get mapped onto the APIs and vice versa. And so we'll start out by talking about the way in which this can be done. And we're going to focus primarily here on Project Reactor, but I'll give some examples in RxJava as well. They're very, very similar. So let's talk about responsive. Remember, the point of responsiveness was not to block and to avoid having the dreaded hourglass or spinning wheel. You want things to be able to come back quickly with a reliable upper bound on latency. And the way we do that is avoid blocking color code at all costs. And that'll be a big issue as we start looking at how this API works in practice. So the idea, the issue we're trying to avoid is blocking. Why do we not want to block? The reason we don't want to block is because blocking, when you block a thread, like waiting for I/O, for example, that ends up underutilizing the number of cores on the processor unless you go to heroic links with like adaptive thread pools. It impedes the amount of inherent parallelism, and it can also potentially complicate program structure. Now, keep in mind the reason why this was a big deal back in the day when reactive programming came out 5 or 6 years ago, whenever it started, was because we were limited at that point to Java and the Java thread model, where it really didn't make sense to have a whole lot of threads. Because remember, threads were expensive. The traditional Java threads, which are now called platform threads, were pretty costly, so you didn't want to create a lot of them. What's changed, and we'll see this will have a great impact on some of the analysis of the pros and cons of the reactive paradigm, is that with the advent of Java 19, all of a sudden, we've got threads galore, and those threads are very inexpensive to create. And so one of the things that we're going to have to be cognizant of is how changes in the underlying virtual thread model make an impact on the decision to use reactive programming. And we'll talk more about that shortly. But back in the day, we didn't want to do a lot of blocking because blocking cost a lot. And therefore, reactive programming models added these operators like subscribe on, publish on, and observe on, and so on, that can be used to transparently avoid blocking color code by running the computations, the events, and so on threads that are in the background in some pool. Another thing to be wary of when you're trying to make your program more responsive is avoiding changing threads excessively. Because if you change threads a lot, that can incur a lot of overhead with respect to synchronization, context switching, the management of memory and caches, and so on and so forth. And it gets complicated. And that's also, needless to say, a source of bugs in concurrent programs written in more old-school, object-oriented styles of paradigms. Once again, we have operators like subscribe on, publish on, and observe on that give you fine-grained control over where the events are mapped to threads. So you get a lot of degree of autonomy to make those decisions, which comes with a cost, right? Like Peter Parker's uncle, with great power comes great responsibility. So you have all these tools to make things very flexible, but you have to know how to work them. Another principle, resilient. We don't want everything to fail when one thing fails. So the way that's handled in reactive programming is by having exception methods or exception operators that make things more resilient to failure. Because if something goes wrong in an asynchronous chain, then you can handle it and adapt or compensate or resume or continue, whatever you choose to do, without breaking everything else. So just because one thing fails doesn't mean all the other threads that are running have to fail too. And you'll see that reactive streams are localized to a single process. They don't work in a cluster unless you program them with things like web fluxes. So this is actually very similar to the way that exception handling works in Java completable futures. I know we haven't talked a lot about that, but if you're familiar with completable futures, basically the same idea. The next principle, elastic or elasticity, which means we want to be able to auto-scale. As load grows, we want to be able to incorporate newer, more abundant resources, like getting more threads out of a set of cores or moving between computations in a cluster or whatnot. And the way this works, once again, is by using different kinds of schedulers. And RxJava has a bunch of schedulers that can be used to indicate where you want your computations to run atop a set of cores. And Project Reactor also has a set of schedulers. For some, God knows why reason, they don't have the same names, which is a little frustrating at times, but they all map pretty much one-to-one in terms of the concepts that they embody. By the way, I have to do a quick aside here. I don't want to get too off the track, but as I've been playing around with ChatGPT, something very fascinating is occurring to me. So when you use ChatGPT and you type in your English language spec and say, please generate me code that does blah, 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 in Java or whatever, it'll generate you the code. And then you say, please regenerate the code in C++, or please regenerate the code in Python, or please regenerate the code in a different Java paradigm, right? Object-oriented versus functional versus reactive versus whatever. And instantly, it does that. And usually it's pretty perfect. It's amazing. Think about what's going on, right? It somehow has a representation of computation provided by English language specs. And then it can automatically and usually correctly transform those things into different language bindings. So it sort of raises the question, what is the internal representation that's this sort of universal programming model of computation that ChatGPT has in its little mechanical brain, its little digital brain? And how is that doing that? Because as humans, most of us probably know a couple of languages. I'm a really good Java programmer. I used to be a really good C++ programmer. So given a computation, if I sit down and think about it, I can usually express it a couple different ways, much like a person who's multilingual can express the concepts in different languages. But it makes you wonder, I don't know how my brain figures this out, but I also don't really quite know what model of computation ChatGPT is using to do this transformation. But it's really cool. And you can imagine as it gets trained to do a much wider range of transformations, it's going to be able to do these things way faster than most people can do, because most of us don't know more than a handful of languages, either programming languages or spoken languages. OK, that's a bit of an aside. The last point here is, the last principle is message-driven. So remember we talked about that being a slightly different way of doing things than the other three principles because it's more of an implementation detail. So the way things work under the hood is that reactive streams and Java internals, like their thread pool mechanisms and so on, create messages and pass them around internally. So interestingly enough, the APIs that are exposed are method-based APIs. But what happens under the hood with those APIs is they actually convert the parameters that are passed in into messages and then pass those messages around to various queues. And it's worth considering, why do they do it that way? So the message passing gives you flexibility, but message passing is also a little bit tedious and error-prone to do. The opportunity for mistakes is rather high. Whereas method-based coding is usually more type-safe and honestly a bit more concise. You don't have to allocate stuff directly. It's all hidden for you. So it's message-driven, but method-programmable. So it's method-programmable, message-driven implementations, which I think is kind of an interesting hybrid approach. OK, so that's the end of the discussion of mapping reactive streams onto reactive programming principles.